and I will be conducting the EECE 1202 Exam 2 review. This exam covers topics from the first exam. After the first exam, the class covered Introduction to Filters, gain equations, and derivations. They also covered Introduction to Microcontrollers, and the professor will be testing them on mostly these two topics, which is what, based on the fact that we have limited time, this is what I'll be able to go over. So mostly I will go over the filters, gain equations, and derivations. Since the introduction to microcontrollers, most of them are notes. I have some of them here. I have some of them right here. Excuse me. All right. What is an embedded system? That's what some of the things that the students are expected to know. They can find this information in the professor slides or in this specific slide. Towards the very end of it, the professor has given the ways, or rather what the professor expects the students to know. They expected to know what is an embedded system, the 4 types of embedded system needs, and know examples of each. They also expected to know the basic structure and characteristics of embedded systems. Microprocessors versus microcontrollers, Arduino versus Raspberry Pi versus a Launchpad. Arduino is a microcontroller. Raspberry Pi is like a mini computer, so that's a microprocessor. A Launchpad is essentially just an Arduino, but that's not open source. Arduino is open source. Launchpad is owned by the company Texas Instruments. Students are also expected to know the definitions of the baud rate. They've mostly seen this when doing their labs and their programming Arduinos. So they will set the baud rate at, say, 9,600. They've also done most of the information on the definitions they have seen in the labs. So based on that, we'll start on the filters. For the introduction to filters, we have All right, I'm sorry, we ran into some technical errors, but we're back. As I was saying, we're going to start on this first example. Basically, from looking at it, one can see that this is a inverting. How do we know that it's an inverting op-amp? That's because the input from V1 is connected to the negative terminal of the op-amp. That's how we know. And from the configuration, we have the RF, which is a feedback resistor, and the input resistor. So this question is asking us to calculate RF, which is the feedback resistor value. The questions have been answered before. Someone had done this before just to make sure, but we're going to go ahead and calculate it. So one thing we do have to know is the equation that that's for this op-amp. It's usually V out over V in is equal to minus RF over RI. This is also equals to the gain in volts per volts, which is also sometimes known as AV from a question. If a question asks and has AV on it, that basically means that it's asking about the gain. So since we're asked about RF, we can change this. We can change this to find the value of RF. So V out, we've been given V out as minus 12.00. Is equals to RF value. Going to leave it as that. Minus over RI is R1. We're given as 5 kilo ohms. And then V in. Where's V in? Oh, we also asked to calculate V in. So I'm going to delete that. We've been given the AV that I was talking about, which is the gain. And from the gain, we can calculate this. It actually makes it much easier. From the gain, we've been given minus 1.20 is equals to minus RF over RI. We don't have RI, we have R1, which is 5. So it's going to be minus 1.20 times 5. You can get out the minuses because they have minus on both sides. And using our emulator calculator over here, we have minus 1.20 multiplied with 5. And you get the value as 6. It shouldn't be minus 6, it should be 6. We took out the minus. And then the value for V1, you can use the same formula for V out over V in. So V out over V in is equals to the gain, which is 1.20. This is the gain in magnitude. We have V out as minus 12, minus 12.00 over 1.20 to find Vn. We have 12.00 over 1.20, and we have it as 10. As you can see, we have both those values correct. As you notice, the person who was doing this failed. The question asked about the face. From looking at it, can you tell why the student failed asking the question about the face? From what we've learned about op-amps, or rather inverting op-amps, we can see that one would go directly to answering the question and saying that it's 180 volts based on the fact that it is inverted. But in this example, it's not asking about the V out. As you can see, the face of Vn, which is something to note when doing the test. It's asking about Vn. So the Vn going in is not inverted. So the answer should be 0. I'm gonna say that one more time because it's a very important question. The phase, the question is asking about the phase of VI. Now, based on the fact that you have limited time during the test, you may go in and since you already know that the op amp is an inverting op amp, and answer the question as 180 volts because you already know an inverting op amp inverts the wave. If you look at it from, say, MATLAB or through an oscilloscope, the input wave looks like a mirrored version of the output wave. And so the answer should be 0. On to our next question. It's also asking about op amps. But for this one, this is a non-inverting op amp. How do we know that's a non-inverting op amp? We know that it's a non-inverting op amp based on the input. The input is connected to the positive terminal of the Vin, or rather the voltage source, is connected to the positive terminal. So for this one, the formula is different. We have V out over Vn is equals to 1 plus Rf over Ri, which is also equals to the gain. And it's also equals to the gain. These two show the gain, different ways of representing the gain. So from our question, we've been given V out as 12.89 volts. We've also have Ri, or our input, or R1, 4.5 kilo ohms. We've also been given the gain. Also AV, which is 3.22 volts per volts. We asked to find RF. So plugging that into our equation, 3.22 will be equals to 1 plus RF over R1, which is the input, 4.5 kilo ohms. So it's in kilo ohms, but you do not have to change it back to ohms by multiplying it by 10 to the third, as long as you keep everything as a constant. Like you do not change one to ohms and the other one leave it as kilo ohms. So that you gotta be notice that. So take one minus 1 from both sides, 2.22 equals to RF over 4.5. And once you multiply this, 2.22 to multiply it with 4.5, get 9.99. The answer given is 10 kilo ohms, but that's just rounded off. We also asked to find V2. V2 is our input. You can get that from this formula over here. So V out over Vn is equals to the AV. V out will be 12.89 over V2 is equal to 3.22. 12.89 over 3.22 will be equals to V2. And get our answer as 4. On this one, we also have a question asking about the phase. Now for this one, you do not have to worry about the answer you give since this is not an inverting op amp. So the signal that goes in will be the same as the signal that goes out. This one is not inverted since it's connected to the positive terminal. But it's also worthwhile to check what the question is actually asking. It's asking about V2, not about V out. So the answer is still 0. On to our next question. So an interesting fact about our next op amp, this is known as the summing. Okay, sure. Okay, so as I explained before, that comes from noticing what type of op amp you're working with. For those who are online, the question asked is, how do we go about finding the phase of the angle that's being asked about? So comparing these two op amps, the first one, we can see that this is an inverting op amp. Inverting. This is a non-inverting. Inverting. Okay, so this one, if asked about V out, the V out will be negative. Question, the reason of that is the V that's going in, the voltage input, it's going through the negative terminal. So that's why that's how you're gonna know that if it's asking about V out, it will be negative. But since it's not asking about V out, it was asking about V in, this was just an error made by the student based on, they probably thought that the question wasn't asking what the question was asking. So it's caution to the students to check what the question is actually really asking. It wasn't asking about V out. It's a trick question, essentially. We have most of those in tests. Is that okay? Gotcha. On to our next question. So as I was saying, this is an interesting OPM because it's not different from the others. The two prior ones that we've seen are different. This one is essentially an inverting OPM, but with multiple inputs. So they're all connected to the negative terminal. They're all connected to the negative terminal of the OPM, but as you notice, they have multiple inputs. So the formula that we use for this one is very much similar to this is a summing amplifier. OP amp. Okay. So the equation that governs this one is V out is equals to minus RF, negative because it's inverting. It's going in, the input that's going into the OPM is being inverted since it's going through the negative terminal. And then it's you get V1 from the first one over R1. From this point, you can see that this formula coincides with this one for the inverting, since you're going to be taking RF over RI V in. This is the same as RF VI over R1, but with a single input. And then it will be plus V2 over R2 plus V3 over R3, so on. It's as many inputs as you have. So it will be minus RF. So on to what the question is asking. The question is asking us to find RF. We do not have RF. We have V out though. V out is given as minus 6. V equals to minus RF. As you can see, I'm writing it down as the formula says. As someone who's doing this for the first time, I would recommend doing this instead of doing the math in your head, since you might mess it up. V1 is given as 10 over R1, which is given as 3, then 8 over 9 plus 3 over 6. Doing this on a calculator. We can cancel out the minus signs because we have the minus on both ends. We have, make sure one more time. V1 over R1, 10 over 3, 8 over 9, and 3 over 6. Gotcha. Then alpha over 3 plus 8 over 9, 3 over 6. Get 85 over 18 to the decimal. That's 4.72. 6.00 over 4.72 equals to RF. .27, and as you can see from the answer here, the answer was 1.27 kilo ohms. On to our next. So as of now, we've covered the 3 basic OPMs that are covered in CE EE 1202. On to our other one. Last one, this is known as a differential difference, OPAMP. Difference OPAMP. And how do we notice the differences? Let's go back. We know the inverting based on the input is connected to the negative terminal. This one and this one, the inverting and non-inverting look very similar. So you have to be very keen onto where the inputs are connected to. The inputs being this symbols right here. And this symbol. It's connected to the positive. That's how we know it's a non-inverting. And it's also connected to the negative. The reason I'm saying this is because the question can be drawn as this way. Where you have the OPAMP, and it's connected as we would expect it to be. You have the resistor here. You have that there. Have the power source, all that good stuff. But the terminals is plus or minus. So you might go in thinking that, oh, the way you expect it to be is, or the way you've seen it in prior examples, is that it's connected to the negative terminal, but this one might be connected to the positive terminal based on the orientation of the OPAMP. That might be something good to notice. And then for the summing, it's basically summing is essentially an inverting OPAMP with multiple inputs. Onto the our last OPAMP, our difference OPAMP. For this one, in general, before we go into the question, the way we know how to proceed with it is if R1 over R2 is equal to RF over sorry about that. It's if R1 over RF is equals to R2 over R3. So if this one over this one, the ratio of R1 over RF is equal to the ratio of R2 over R3, then the formula we use is V out is equals to RF over RR, or R input, or R1, V2 minus V1. So notice it's not V1 minus V2, as one maybe expect from other problems. That's a tricky part in this question. One way to memorize it would be mostly through multiple practice problems. And also noticing this, that it's the first resistor over the feedback resistor, okay? This is usually given in the notes. At this point in this class, for EECE 1202, they do not go deep. It's a long way to derive this formula. So this is taken as a standard. For us to be able to use this formula for a difference OPAMP, this ratio has to be true. Yeah, that's just given for at the moment. But as you progress on taking higher analog circuit classes, you'll learn to understand why that is the case. The question was how do we know if, why is it R1 over RF? And as I said, we're going to learn that in future classes. So proceeding to the problem, we are told that R1 is equals to R2. And we are also told that RF is equals to R3. So given this information, that R1, RF and R3 are equal, and R1, R2, then it's given that the ratio is going to be equal. So we can use this formula. We can apply this formula. Equals to RF value is 4 over RI. We do not have it. That's what we're looking for. V2 2 minus V1 8. So that will be minus 6 times 4 minus 24 over R1. And we have been given V out. So this V out will be this. Minus 24 over R1 will be equals to V out. V out being minus 3.60. We can cancel out the minus signs because it's given. So it'll be 24 over 3.60. Given as 6.67. And as you can see from here, that is our answer. Any questions so far? Okay, we can proceed. I'm going to skip over this question, asking about complex numbers. You have covered this before. And for this session, I am planning on concentrating on the stuff you've covered after exam 1. We will, however, come back to it, but a quick refresher on this, on how to go about solving this question. We've been given these values of the complex numbers in rectangular. For us to be able to solve it, we have to convert them. For us to be able to divide them in the way they are, we have to convert them into polar. How to convert them into polar would be, so this represents, you would say it presents the x, the positive, or rather the real part, and this is the imaginary part. But thinking about it from questions we've done before, this would be the x and this would be the y. So you can basically find, you're going to have to find the values in this format. This is the angle, and this would be the value. Let's call it x, for you to be able to divide it. And then it will be y, and then theta 1, theta 2. For you to be able to say find x, it would be 8 squared plus 3 squared into square root. And you do that for all of them, including the signs. So then you'd have to do, once you're done with that, you find the real part. And for the angle part, you would tan theta is equals to y over x. So this part over this part, including the minus signs. So an interesting fact over here is that I would recommend graphing them in the xy plane. So this one would be -5. So -5 would be here, and positive 11 here. So it would be in this quadrant. Most of you have seen this. All students take calculus. It will be in this quadrant, but once you do it, it will bring itself in a different quadrant. So you will need to adjust for that, either -90 or add 90. But as I said, we'll come back to that once, because we have limited time. If we have enough time, we'll come back to that. For this one too, we have the components connected in parallel. We have the resistor, have the capacitor, and we have the inductor. This two, you might have covered it before exam 2. But we'll go through this one shortly. We will not process the values because it might take time putting them into the calculator, but I'll give the formula on how to go about it. The question is asking us to find phasor techniques to determine the current supplied by the source. So for the current, we are going to use Ohm's law. V is equals to IR. I representing the resistance, I the current. So I is V over R. However, here we are not just looking for the resistance. We do not just have a easy circuit with a resistor connected. We have a resistor, we have a capacitor, and you have the inductor. So we have to, for R, we have to replace it with Z equivalent. So we have to look for Z equivalent. We've already been given the volts. We've already been given the volts. Over here in phasor, we have it as 15 with 0 degrees. So for us to be able to find the Z equivalent, having been given them in the way they've been given in parallel, it would be 1 over R plus JWC plus 1 over JWL. 1 over R representing the resistor, JWC representing the capacitor, and 1 over JWL representing the inductor. So once you find this, once you put in the values, and all these values are given, the value for W is given here. The value for the capacitance is given here. You would have to convert this, however, into farads. The value for W is given, the value for the inductor is given. You'd plug in the values and basically just divide the voltage given with the resistor. We'll come back to that if we have enough time. Let's go to this question, asking about OPMs. It's asking what type of filters or what type of amplifier is shown in the figure. So based on what I explained before, we look at the incoming voltage source. Where is it connected to? To what terminal is it connected to? For this one, we have it as V2. and it is connected to the positive terminal of the op-amp. And that's how we're able to detect what type of op-amp this is. And since it's connected to the positive, it's non-inverting. We also have a question says that if we provide DC sources for V source positive is equals to 4 volts and V source negative is equals to minus 4 volts, the amplifier in the figure, what will be the maximum and minimum values of V out? So in an op-amp, which students taking EEC 1202 may have done a lab on this using an op-amp, they've seen from the figures drawn, other than the way it's drawn normally, it has 2 rails over here. It has a positive rail and it has a negative rail. So these rails act as an upper and lower bound of what V out will be. So say they're set at say 2 volts, and this one set as minus 2 volts. The V out cannot go above 2 volts or go below minus 2 volts. That's essentially it. So when giving the answer, the maximum will be that which is given. So for those who have done this lab or may not have done this lab yet, you connect, these ones are DC sources, direct current. Here for the V2s and the V1s we've been observing, all of them have been sinusoidal in nature. So that's where you connect them to a oscilloscope and you're able to view the sine wave incoming. For this one, it's given as a DC current, as we're told in the question. So the maximum V out will be 4 volts. The minimum will be minus 4 volts. And the VS plus and the VS minus are known as amplifier rails. Go on to the next question. So I would say this is part of the. So our next question, this would be the challenging part for most students taking EE 1202 or seeing these equations for the first time, since the op-amp given has a resistor connected to it from the V out. So for this question, it's asking us to calculate, assume VS is equals to 5 volts, V source, 5 volts peak to peak, meaning it's a sinusoidal. R1 given here is 1400 ohms. R2 given is 4500. R3 is R3, 8500. And find the values of I1 highlighted here, I2 and I3 and I out. So for the op-amp has 2 golden rules. So when observing the first time you see this question on a test, the first thing you should think about is the first 2 golden rules. Without those 2 rules, you cannot solve this question. So what are the 2 rules? One thing we planned about an op-amp, or that is given by nature at this point, before we go on in future classes, we'll understand why this is the case, is that the voltage here, let's call this VA, is the same as the voltage here. That's just given at the inputs of the negative and positive side. So VA is equals to VB. That's given as a rule when solving these type of problems. Another rule is that at the incoming current, this point, no, sorry, at the point, I can enlarge this. Let me delete this for demonstration. At this point, there is so much resistance that the current here is 0. It's seen to be 0. It's not 0. It's really small, that it's in negligible. So will be our approach here. We first know that VA is equal to VB, and that the current over here in this section is negligible. So that's our second step after realizing that will be viewing what type of op-amp we have. From here, we can see that the VS, V source, is connected to the negative side of the op-amp, which means that this is a inverting op-amp. Also, the second thing we have to do now before we go on to find the different currents we've been given is to find V out. So since this is an inverting op-amp, and a student who's doing this problem should already first thing should do is find the value for V out using the formula given. V out given as V out is equals to minus RF over R input multiplied by Vs. So our RF is 4,500 minus 4,500 over our input is 1,400. All this multiplied by 5. So that would be 500 over 1,400 multiplied by 5. Value as a decimal. That's minus 16.07 volts. This is our V out. Please. I'm going to do it over here. Our V out is given as minus 16.07 volts. So the next thing we do is that we employ KCL, Kirchhoff's current law, to find the different current. So we already know that. So here, our current will be 0 at this terminal. And our voltage too will be 0. Why will the voltage be 0? That is because this is connected to ground. VB is connected to the ground. So our voltage will also be 0. So the first thing will be developing the Kirchhoff's current law. The current I2 and I1, since the current here is 0, and the direction of I1 is into the OPM via the negative terminal, the feedback current, or rather the current via the feedback resistor, is also meeting at this node. And the current given here is 0. One of our golden rules. We'll have I1 plus I2 be 0. So that's our first equation. Our second equation will be for I3 and I2. I out, for calculating I out, will be I out is going this way, and you have the current via the I2 going up and going down. So KCL, current going into into our node is a current going out of the node, or rather the current at the node is 0. So I out will be I2 plus I3. The reason why this is because the current I out is going into the node, the current I2 is going out of the node, and the current I3 is going from the node. So from looking at this, before we touch I out, we can see that we can calculate I1 easily. This is because we have both the voltage input and the resistance. So this one will be, and we also have to notice the directions. So let's say, for example, a student didn't take care of the directions. That would be a problem because they would minus the wrong one. So you find the students probably saying 0 minus Vs, but this is not the case given that the I1 is going in this direction. So it would be Vs, which is 5, current I1. Vs, which is 5 over 1,400. 1,400. Given as multiplied by 1,000. Would be 3.57 amps. And right here would be 3.57. milliamps. So given from this equation that we have two unknowns, we already have one of the knowns, that I1, replacing I1 in this equation, 3.57 plus I2 is equals to 0. That means that I2 has to be minus 3.57. 3.57. So we already have I2, find I out, based on this equation. So that would be the approach that I would give students. Instead of first going to find I out, since this is an easier way, we've already been given the direction, we already have the voltage, we already have the resistance. Using V is equals to IR, our only unknown here is current. So first find I1, because I1 will allow you to find I2 quite easily without having to go through the different equations. With this, don't need it anymore. And then we'll go to find we'll find I3. So we already have I out is equals to minus 3.57 plus I3. So the other equation we have is this one. We also have the voltage out over here as minus 16.07. And since all this is connected to ground, the voltage here is 0. So the voltage difference here is minus 16.07 and the voltage on this side is 0. So since current is for I3 is going in this direction, you have minus 16.07 minus 0 over 8500 to find I3. Minus 16.07 over 8500 is by 1000 in milliamps, minus 1.89 minus 1.89 milliamps. Oh, we did this wrong. Yes, it is not amps, it's milliamps. First, get back to that. And so we have I3, we have I2 from our first equation. We don't need to do any more calculations. So based on this equation, I out is minus 3.57 plus minus 1.89. That would be minus 3.57 plus minus 1.89, giving us minus 5.46. Our I out will be minus 5.46 milliamps. So I1 was, what was it? 3.57 milliamps. Our I2 was negative of that, 3.57 milliamps. Our I3, just found it out, was minus 1.89 milliamps, and our I out is minus 5.46. See if we got it right. Our I1 is 3.57. Our I2 is minus 3.57. So this student failed on the I3 and I out, but I have the correct answers over here on the side. Our I3 is minus 1.89 and I out is minus 5.46. So again, going through this again, once given this circuit, first thing to identify is what type of op-amp we're using. You'll see this, the reason as to why I'm insisting on this on our next problem. The next will be to find V out once given the op-amp. Once you already have identified what op-amp you're using. And then the next will be to apply KCL on the nodes to find the different currents. And once you're done with that, as long as you have the correct equations, you can go and proof check your equations. Because if you find, let's say, I3, as you find all the values and the equations you made, as long as you made them correctly, you can plug in the values to see if you did it right. Go to our next problem, a similar problem to that. This problem was not included into our notes, but I saw it fit to include it. Then some student might run into it during the test. So the reason as to why I was insisting, it's really important for us to know what type of op amp you're using. If you look closely to this one, a student who may not be as familiar with op amps might think that so a typical op amp, or rather how we're introduced to op amps, is that we have the voltage source minus input minus plus. And you have a resistor here. My drawing's not that good, but it's just for demonstration purposes. So this is a typical op amp configuration. So as you can see, most op amps that you have seen before up until this point have been connected to the negative terminal. Unfortunately, in this question, the Vin is not connected to the negative terminal. It's connected to the positive one. So having seen an op amp not like this before, you might forget if you haven't done practice on it. So that's why we're going to do this question. So see how the op amp, the I out, or rather the circuit in this section over here is the one that's connected to the minus one. So from the given circuit, we have to identify first what type of op amp you're using. This is a non-inverting op amp. Non-inverting. So you have to first find V out. V out will be 1 plus RF over RI. This is the equation for non-inverting multiplied by V in. So V1 plus RF. So our RF here, another interesting thing is that the RF feedback resistor for an op amp is always connected to the negative terminal, regardless of whether the V or the voltage input is connected to the positive one. So as I said, the typical op amp configuration is that you have the feedback resistor and the voltage connected in a way that seems like what you would call an op amp. But this one, the feedback resistor is over here, but yet the input is over here. So that's something to notice in this problem. So our feedback would be 3200, and then this will be our input over 1600, our R input, Ri, and then V in will be 6. We'll plug in these values into our calculator. We have 3200 over 1600 multiplied by 6, and you have 18. So 18 volts is our V out. We'll use a similar process to it. So V out is given as 18 volts. So in most of these problems, at the level you are at the moment in this class, you'll be given the directions of the current. So we have I3 going this direction, I2 going in this direction, I1 going up. So this is something that you just take it the way it is at the moment. Don't ask why we have current going from the ground up. That might confuse you at the moment, but as I said, as you take more classes, you will realize why this is the configuration that's drawn in this case. So V out, I forgot something very, very important. We also have to realize when solving these problems, the first one, the one we solved, and the second one, we have to know the 2 golden rules. So without those 2 golden rules for an op amp, we cannot approach these problems. So the golden rules is that, see how I've written 6 volts here? There is no voltage source, but it's still 6 volts. Don't ask why that is the case at this moment. That would be my advice. I mean, it's good to be curious as an engineer. You all are engineering students, but at the moment, just take it for what it is. You will realize why this is the case later, based on like the circuit that's in the op amp that allows for this to be the case. And then you have 6 volts. And you also, so at this node, you have 6 volts too, since there's no component here in this section. And the current will also be 0 at both. So now that we know that, we form our equations. So I out will be equals to I2 plus I3. Also, I1 plus I2 is equals to 0. So for us to be able to find I1, it will be the current is going upwards. Notice that it's not 6 minus 0. We'll do it as 0 minus 6 over 1600 plus I2, 18, since the current is going in this direction, minus 6 over 3200. And this should give us what? Is that right? Give me 1 second. Let's see if this is right. I1, I2, and I out. There's 0. Plug the values in. 0 minus 6 over 1600. Get that. And you have 18 minus 16, 18 minus 6 rather, 18 minus 6 over 3200. So if you add these two, minus 3 over 800 plus 3 over 800, you'll get 0. So our I1, let's get the values. Decimal. 5,000. 3.75. So I1 will be minus 3.75. I2 will be 3.75 milliamps. And this one will also be milliamps. Sorry, excuse me. So for our I out, same case, plug in the known 3.75 milliamps plus I3. So we just need to look for I3 at this moment. At this node, the voltage, since it's connected to the V out of the op-amp, will be 18. So, and the direction of the current is downwards, will be 18 minus 0 over 5400. As that multiplied by 1000, 3.33 milliamps. But this was not a question among the questions I had given. This was just a question I decided to show you all, since I believe most of you, if not all of you, will find either of these two configurations on your test. So those are the two approaches that we use to solve this problem. On to our next problem. This question looks familiar to the one we did before. So this one, just that this time our components are connected in series. When our components are connected in series, we used we still have to use V is equals to IR formula, but in this case we have more components. This is a capacitor, this is a resistor, this is an inductor, and so we have V rather is equals to I Z equivalent. We have to calculate Z equivalent. Z equivalent for components connected in series will be the resistor value plus 1 over JWC plus JWL. This is for the inductor. This is for the capacitor. And this is for the resistor. And once you find it, our question is also asking, unlike the question before, this one is asking about the voltage across the different components. So since we are employing complex math, which may take us some time. I'm going to leave it at this. This is the formula you have. You just plug in the values that you've been given. So VS, as you can see, VS is given as 6 cosine 3t. Essentially what this means, you just take 6 to 0. It doesn't have a phase shift. So it will be just the amplitude represented by 6 and 0 degrees. And that you'll take that as your V, as your voltage. Now, once you find Z equivalent, you'll just do V over Z equivalent for the current. If we've been asked the current in the question, but we haven't been asked. We just been asked to find the Z equivalent. So you just do this math, complex math. Once you're done, for the capacitor voltage across the different components, start with the voltage across the resistor. The formula for the voltage across the resistor will be V source given in the question. Let me write it down here. Voltage across the resistor will be V source multiplied by the resistor value over the Z equivalent that you calculated before. And that will be the same for voltage across the capacitor will be V source over the Z for the capacitor, not for the whole thing over the Z equivalent. And how to find Z for the capacitor? It's essentially just this component, not having been added to calculate the Z equivalent. And for the voltage across the inductor, it'll be the same formula. Vs over Z inductor over Z equivalent. That is essentially it. We might come back to this if we have enough time at the end. This is another very important question that I do not think if you miss it on this test, you'll definitely find it on the other test. This is a question about filters. The questions we've been doing before have been about OPMs. This one is about filters, and you may have done this on a lab before. Designing a high pass filter. This is a low pass filter. And also took notes here to also explain how to go about solving for the different questions asked. So we've been given the VS as 8 voltage peak to peak, and the capacitor value as 4 nanofarads. The resistor value, feedback resistor as 700, and the resistor input as 2000 ohms, and the this value for calculating, you're going to use it in calculating the cutoff frequency as 2000. I forget the name. It's a W. Okay, let's start with the first question. So it's asking what type of circuit this is. How we go about knowing this is unlike before when we checked just about whether the VS is connected to the negative or positive. Since this is not just a regular OPM, this is a filter. Low pass filter is connected in this manner, where we have RF and CF. Now, one might think, or one may decide to use the acronym because this is connected as a H, right? Looks like an H of some sort. One may think to call this a high pass. This is not a high pass. This is a low pass filter. A high pass filter has, or rather has this configuration. It has the capacitor in series with the R input from the input side, and then it goes, then so on and so forth. But this configuration here is essentially where the capacitor is for a high pass filter. This is capacitor input. And for a band pass, so this is a low pass filter. Essentially what it does, it allows signals that are lower than the cutoff frequency to go through. High pass allows signals that are higher than the cutoff frequency to go through. So this allows for higher signals, higher than the cutoff frequency, CF, standing for cutoff frequency. This one allows for lower signals with the value that is lower than the cutoff frequency, and the bandpass. This is a bandpass is essentially a combination of these two features. So a bandpass will have this configuration here, and it will also have this configuration here. So you'll have both in the same circuit. So you have a probably right over here, addition to this. Here, minus, plus, that. And so this is RF, this is RI, and you have the capacitor here. So this is a bandpass filter. So on to our problem. Get this. Is anyone taking notes? Okay, gotcha. So we've already identified that it's a low-pass filter based on the configuration. At this moment, one, you can make an acronym based on letters you know, but just make sure not to confuse this as a high pass, because if you do confuse it as a high pass, then you fail the whole question, because any value you calculate before or below this one, you calculate it as a using the formulas for calculating a high pass. So on to finding our cutoff frequency. So the formula for calculating our high pass frequency, I had that written down somewhere. Sheets. Okay, it'll be 1/2 pi RF CF. So you're given this as a frequency. But look, we've been given W, this value, W is usually equals to 2 pi F. For you to find the frequency, you have to divide this by 2 pi. That's what we're going to do here. Since we have to use it here in form of, we have to use it, or do we? We actually do not have to use it at the moment in this problem. We'll use it later to calculate the cutoff frequency. So, or to calculate another frequency. 1/2 pi times RF, which you've been given. Give me one moment, my laptop, to connect my laptop, it's dying. Very good. So 1/2 pi times RF feedback is 700 multiplied by CF, value for a capacitor. It's given in nanofarads. You have to convert it into farads. So 4 times 10 to the minus 9. Plugging this into our calculator. 1/2 times pi times 700 times 4 times 10 to the minus 9. And you have this value as 56,841.05. 5,600. Let's see if it's the correct answer, and it's the correct answer. 5,608.41. For this formula, you just have to memorize it. There's no way to derive it from the given problem. It's 1/2 pi RF CF. If you want to find, say, FC in rads per second, you just have to do 2 pi F, which is the same as W is equals to 1/RF CF. So you just have to manipulate it. You manipulate it using this equation. On to our next problem. It's asking what the circuit does. As I explained before, a low-pass filter will allow for signals that are lower than the cutoff frequency. So signals that are lower than this frequency, FC, to go through. So if we were to draw a Bode plot is a plot that allows for us to be able to simulate this type of circuits. A low-pass filter will look like this, or something like this. The cutoff frequency will be here. It will allow signals here to go through. But let's say if a signal is higher than the cutoff frequency, so our cutoff frequency is at 56,000, or rather 56.8 kilohertz. It will, let's say it's at 60,000, or rather 60 kilohertz, and it's say somewhere around here, it will be attenuated. This is called the attenuation region, just for the vocabulary use. To go on to find the nominal gain. The nominal gain means the gain in the past. So this, as I said, this is the attenuation region, attenuation zone or region. This is a passband. Question is asking, what is the nominal gain of the filter in dB in the passband? That means that we have to find the gain in this section. So the gain in this section means that the frequency, or rather, the frequency of the input will not be attenuated. It will not be cut off by the filter. So for that, we just calculate the gain normally as we would calculate for an OP amp. So the gain, asking for the nominal gain, will be equals to, and since this is an inverting OP amp, we'll use the equation for calculating the gain for an inverting OP amp minus 700 over 2000. We have it as minus 0.35, and this is in volts per volts. Notice the units; it's in volts per volts. But our question is not asking for the gain in volts per volt; it's asking for it in dB. dB is a way to show, or rather to simulate the Bode plot or the values from an OP amp in a logarithmic scale. So logarithmic scale allows for us to simulate signals as low as, say, 100 hertz to signals as high as a value hertz. So these two cannot fit in a linear scale as we would draw x via y axis. So it requires us to use a logarithmic scale. And the logarithmic equivalent of gain is dB. So how to convert that into dB? You have to know this equation, which you may have seen before. It'd be 20 log to the base 10 of the gain in volts per volts. However, if you plug, say, 20 log 10 of this value as it is into the equation, you'll get a non-real answer. We're not going to plug it in because of the time. However, if you do plug it in, you'll not get an answer. So you have to know that once you find the gain this way, the value that goes in here is the value without the minus. It's essentially this, the gain volts per volts, the magnitude of it, not the direction. So the magnitude is 0.35, so it'll be 20 log 10, 0.35. For 20 log 0.35. And we have it as minus 9.11 or 12 dB. And once you come here, you'll find that is our answer for question 4. On to question 5. For question 5, we'll ask, what is the nominal gain of the filter in dB at the cutoff frequency? So for most of you who are taking this class, this may be your first time seeing all these terms. So an insight to this specific question at this specific point where we are at is that when it is asking for the nominal gain of the filter in dB at the cutoff frequency, it helps to first understand what it's asking for. It's asking for the gain. Nominal means it has its meaning, but we can choose not to focus on that right now. It's asking for the gain of the filter in decibels in the logarithmic scale at the cutoff frequency. So before it was asking for it in the passband. This is the passband. So it's asking for it at the cutoff frequency. So the cutoff frequency is this region, close to it. So where the signal will be attenuated. So how do we do that in dB? So you can choose to go a longer route. The longer route will be where you have to calculate the gain using the frequency. It's a longer formula to go on how to go about it. However, I wouldn't advise going that route. It helps to understand that in dB, the nominal gain of the filter at cutoff frequency in the pass, so the gain in the passband and the gain at cutoff frequency differs by 3 dB. So again, at this point, it might sound confusing, all these terms, but just take that as something that just happens. I know that's not an engineering way of describing it, but take that as something that just is the case that the difference from the nominal gain of the filter in dB in the passband and at cutoff frequency will be 3 dB. So how would you go about doing that? So we already have minus 9.12 here from solving using that route. Instead of going through the longer route of having to look for, because what you'd have to do before I tell you what goes on, since in case you forget, is that you already have the cutoff frequency here, 56,841. So you would have to find the gain in cutoff frequency, which would be ZF over RI. Why ZF? ZF is equals to, since they're connected in parallel over here, you might notice that we did a question like this, where we have the capacitor, RF, and inductor connected in parallel. It's using the same way of calculating ZF. It will be 1 over R plus JWC. So for ZF, you'd have to calculate this to find, because of this right here is why you'd have to go through this longer. So you have to do, you have to input the values for the RF. So you also have to find the 2 pi frequency, cutoff frequency, to find that C. You also have to find CF. You have to do the complex math for this. And then after you're done with the complex math for this, you have to go back to find the GCF. And once you've done finding the GCF, you have to also go plug it into the log 20 log 10. And there's a lot of opportunities to make mistakes. So at this point, it helps to understand that the difference, as I said, I'll repeat again, for the dB of the nominal gain in the passband and the cutoff frequency is 3 dB. So what do you do having the gain in the passband? You just minus 3. So it's in the passband going at the cutoff frequency. You just minus 9.12 minus 3 dB, which will be minus 12.12 dB. And there you have it. It's an easier route to finding and solving for that instead of like going through this long route. But let's say in case you forget that, you don't know whether it's to add or subtract, because you will get it wrong on the test. You can go through this route if you have time. So on to our next question. What is the magnitude of the output voltage V out at the cutoff frequency? So something else that might be helpful, the reason that's why you would go through this route would be for this next question. Magnitude of the output voltage V out at the cutoff frequency. Because once you find the gain at the cutoff frequency, you can just do the gain at the cutoff frequency would be ZF over RI. But V out, we also know V out over R V in is the same as this, right? So gain will be that, and then we have V out over V in. So we are being asked about to find the V out. However, we also have another way to go about doing that using math. So we know that we've been given the magnitude of the voltage V out at the cutoff frequency. We know we've been given the gain at the cutoff frequency. We already found it by minusing 3 dB, so it's right here. So minus 12.12 dB gain in the cutoff frequency. I can see it. Okay. So we have minus 12.12 minus 12.12 dB. So in dB, we know the formula for calculating that will be 20 to the log 10 gain in volts per volts, which is equals to is equals to the gain in dB. So we already have 20 log 10 gain in volts per volts is equals to minus 12.12 dB. So from the logarithmic way of analysis, we know that this can go here, right? To the gain to the 20 to the power 20 log 10 gain volts per volts to the power 20 is equals to minus 12.12 dB. Here we also know that from, let's say log, we have log A, B is equals to C. We know that A to the power C is equals to B. So this to the power this is equals to this. We can apply that same analysis here. 10 to the minus 12.12 is equals to gain in volts per volts to the power 20. So we already have this value. We already have that value. And one thing we can do is that we can raise both sides. Since we're not doing anything wrong, it's just math. We can raise both sides to the 1/20th. And both sides to the 1/20th. We're just doing the same thing on both sides. We're not like changing the math. So once we raise this side to the 1/20th, it just cancels. So plugging this into the calculator. So this math where you have m to the a to the b, you just multiply a to b and b. So you just do 1/20 times minus 12.12. Minus 12.12. You have that, and then you have 10 to that, and you have this answer. Gain in volts per volts is equals to 0.25, say, volts per volts. So that's an easier way, instead of like going through the long route of having to find the gain at cutoff frequency, applying this complex math. If you know this math of logarithm, you can easily find the gain per volts per volts. But let's not get ahead of ourselves. Let's see if we actually got the answer. So since we have the gain, then this is at cutoff. Gain volts per volts at cutoff frequency. So 0.25 is it. I'll delete this. If you didn't get that, you can rewind the video. 0.25 volts is equals to V out over Vn. And this is a magnitude. You may wonder why we got it as positive, since the gain of a inverting op-amp is negative. But remember, when looking for the gain in dB, you have to find the magnitude of it. So that's why we got it back as a magnitude. We didn't find the negative. So in this case, we'll use we have Vs as 8, 0.25 is equals to V out over 8, right? Those are, yeah, that was it. And so it'll be 8 times 0.25. 8 times 0.25. And you have it as 2. Looking at it here, it's not much of a difference. It's 1.98. The V out is 1.98. 1.98, if you round it off, it'll be equal to 2. And the answers given on McGraw-Hill has the 2% tolerance. But also remember, throughout the math, so like here, when we got here, I had to do it to 0.25. So that also made this answer for 2 here change. So that may be an issue, but if you follow through that process, you don't have to go finding through crazy math. I know we only have 5 minutes left, but I'm going to explain this question real quick. So RF and RI have 10% tolerance. So the meaning, or rather what it's trying to say here, it's that it can go up to, say, the nominal value. I'm going to delete some of these to make space. So RF and RI have 10% tolerance. 10% tolerance means, let's say RF is set at, say, 2. It says it can go as high with 10% and low with 10%. So it can vary within a 10% difference. So 10% difference would be 0.11 times 2. Is it? No. It's 1.11 times 2 to find the higher bound, and 0.9 times 2 to find the lower bound. So what is the maximum value of the gain in the passband? So in the passband, you're just doing RF over RI. So for you to find the maximum, what do you think it has to be if you're finding RF over RI? RF has to be the highest. So you're going to take the higher, You're going to take the higher of the percentage to make 700 onto the higher note, and you're going to take 2000 in the lower note. So you're going to take, so instead of it being 700 over 2000, you're going to do 10% more on 700. Sorry, that's 7,000, and 10% less on 2000. That way you get more range in the values, and so that will be it. That's how you'll be able to find the gain in the passband max in voltage per volts. Notice how it's not, you don't have to find dB. I know you've been doing dB for the past 2 questions. You might be conflicted to put it in dB, but you don't have to worry, since in this case, if it's the same, in McGraw-Hill, the values have already been put in for you. I'm going to skip this question since you've done it before. This is no more circuit questions, current going around the resistors, since we do not have times, because I want to explain this question, which is something you learned recently. This one too, I believe you might have done it before in exam 1. I'm going to explain it real quick. So you have done this plot where you have minus cosine, minus cosine, let's say x, cosine x. Okay, you have sine x for some reason, and you have minus sine x. So when doing this, you have to convert these values into phasor values. So for this one, it's already in cosine, so you don't have to worry about it. But the first one you've been given, it's in sine. So you have to first convert it into sine so that you can add them, right? So for this one, to convert it directly, it would be 30 minus 45. 30, the amplitude, and minus 45, the phase shift. This one, however, is sine. So you have to do 34. 34. So 34 is not changing. But notice if you do it directly without looking at the cosine, whether it's cosine or sine, you're going to do this, and you're going to try, and because you cannot add it in the way in polar form, you have to convert this into xy axis, and then add them, and then put them back. Put the value for the real part of the number here. So, real part of the number here, and the complex here. But notice you'll be wrong because you did not consider whether it was a cosine or a sine. So for you to be able to convert this into cosine, it goes in this direction. So from sine to cosine, it has a 90-degree difference. So you'd minus 50t, it'd be 30 sine 50t minus 90. Or no, sorry, I'm confusing you. Cosine. Now it's cosine because you've minus 90. It was sine. Going to cosine would be minus 90. If it was minus sine and you have to go to cosine, you have to go all the way around. You cannot take a shortcut and go back. You'd have to go all the way around of it. That makes sense. And you can review that. I believe you've taken notes on this before. You can review that from your notes. To explain this question real quick, we're already at 7. This review was supposed to end at 7. I'm sorry for keeping you. So this is the board plot. This board plot, looking at it, you might be confused, but just think about it's just a representation of what the filter does. This is the attenuation zone. Attenuation zone is where we have the slanting attenuation. Here's the cutoff frequency where it should be, and then this is from here going on forward. It's the passband. So since this is a passband and this is attenuation region, that means it allows for frequencies higher than the cutoff frequency. And so that's where we have the high pass filter. That's why it's named as a high pass filter. So if it was different, it was a different one. If it was this or this, that means this is a band pass. This means this is a low pass, since it's allowing frequencies lower than the cutoff frequencies. For you to be able to find the value CI, so that will help you be able to find the different values. Where to go into this section real quick. What this for? For the prime. So since this is a high pass, this would be the configuration of a HAP. I believe I had done this before. So this would be the how you draw it out if you wanted to find the different values. And for you to be able to find, so we've been given the amplitude, or no, the gain in dB. You've been given the RI. We've been given the VS, V source. So here, plus minus 3 volts per volts. And we have the amplitude, the gain in dB, the cutoff frequency, and the resistance. It's asking for all these values. What I'm going to do with this is I'm going to post this question on the Discord channel, since we're already out of time. I have to be somewhere at the moment. I'm sorry, I know this took too long. I did not anticipate for it. As you might have all tell, this is my first time doing a review with IEEE. This is my first time being a tutor there. But I believe all of you are on the IEEE Discord channel, yes? In the IEEE Discord channel. I'm going to post this question, and I'm going to explain it, the different sections on how we go about it, if that's okay with you all. All right, thank you all for coming. If you have any more questions, definitely do post them on the Discord channel. I will be able to help you with that. Any question you may have on as far as this class is concerned. Thank you all guys for coming.